We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRE helps formalize industry codes and standards. ISHRE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRE organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, ACREX India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision-makers in the industry. The ACREX exhibition is now growing from HVAC&R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry, all at one location. Our chapters organize several other popular events like ACREConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A Quest, a prestigious the transformation of the budding engineering professionals. ISHRE provides a platform to potential employers to select student members for careers in HVAC and our industry at the ISHRE Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of ISHRE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. ISHRE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation. To enter and explore the universe of the Indian HVACR industry, log on to ishre.in that unfolds a panorama of information. Let us engineer a sustainable future together through ISHRE.
Very good evening, sirs. Very good evening, everybody. Thanks all the attendees, all the panelists. As we know that today we will cover the topic humidification and psychometrics. And for this we have expert speakers Mr. Dawebul and Mr. Aswani Anand. This program is organized by Delhi chapter of ISHRE, is sponsored by Condor and supported by ISHRE India chapter, Raj Patodara chapter and Premjan Memorial Trust. So, without delaying, I request further Mr. Vaibullah Siddiqui, Chair for Knowledge Series for Delhi chapter of ISHRE, to proceed this program with the introduction of the speakers and all.
Thanks, Mr. Tapas.
Yeah, please proceed, sir. Over to you. Thank you very much.
Thank you. I'd like to welcome all the participants who have joined in for this very important topic today. And we know this humidification and psychometrics, this is a very, very, very interesting and very knowledge-giving topic here. And this webinar is being supported by Ms. Condor, which offers the humidity control solutions for industrial and for other, pharmaceuticals, others, tobacco, all industries. And this company Condor is headquartered in Switzerland, with its offices across the world, in Asia, in Europe, in North America, with 750 employees. So for the presentation, we have two very senior professionals from this company. One is Mr. Dawebul. He's application manager, Condor Global Sales, and Mr. Aswani Anand is business development manager, Condor India. Mr. Dawebul has been with this company Condor for last 23 years, and he has been involved in many projects over the time, covering applications such as tobacco, data centers, healthcare, pharmaceuticals, textiles, office, and he's an expert in humidity control. You have any problem, and he can give a best solution for that problem as far as the humidification is concerned. So his profile is you can say for humidity control, dehumidification, etc. He's the expert in that. The other speaker here today is again a very senior person from this company, is a business development head manager, Mr. Ashwini Anand. Mr. Ashwini Anand also is 20 years experience in HVAC field, and he has also done projects in oil, in gas sector, pharma sector, tobacco, data center, etc. And these two are very senior and very knowledgeable persons. So the today's topic of humidification and psychometrics, humidification, is so critical in industries especially, because if the humidity increases in some products, it creates a problem, and if the humidity decreases in different products, it creates a problem. Like a printing press, if you go to printing press, we need a very controlled humidity, otherwise the ink spreads. And if you go to the textile, it is opposite. If the humidity is less, the threads break. So this is a very, very interesting topic as far as the industrial application is concerned. And psychometrics, it is there will be no air conditioning and refrigeration without the psychometrics. So this is the overview, and I would like to hand over to Mr. Ashwini Anand to take it further.
Thanks, Mr. Siddiqui. Thank you very much.
Thanks,
and and a warm welcome to everybody, and very good evening to joining Delhi chapter of ISHRE for this webinar on humidification and psychrometrics. This is Ashwini Anand. I am a business development manager for India operations and taking care for the humidity control solutions across India and the neighboring countries. And just give me a brief about the Condair, as Mr. Siddiqui has briefed everything about us. But let me give a little brief that Condair is serving in the industry for the humidity control solutions from more than 70 years across the globe. And where air caused the problem due to the moisture, we are the solution provider for that. We have 3 manufacturing facilities based out in, one is in Ottawa, Canada, the another one is in Germany, Hamburg, and the another one is in Beijing, China. So we are the solution provider for humidity control solutions. And now I will hand over this webinar to Mr. Dave Bull. He's our senior application and product manager based out in UK. And I based out here in Delhi and covering India operations from Delhi itself. So Mr. Dave, please take it further for the webinar on that.
Thank you for the introduction. And firstly, thank you all for your time today for coming to see what you've got to talk about, which is the interesting topic of humidification. Okay, so topic today is humidification and psychrometrics. Thank you for the introduction, Ashwini. My name is Dave Bull. As was said, I've been applications manager with Condair for 23 years. So I have a wide range of experience in the field of humidification. Condair, as Ashwini said, we have our own sales organizations in many countries across the world, 4 different manufacturing sites currently, and where we don't have our own sales organizations, we have a network of distribution partners, including 2 in India, who I'll talk about a little bit later. So just to look at the learning objectives for today. So firstly, we'll talk a little about why humidify, so why humidity control is important, and what industries and areas we may consider doing that. Then we'll talk about the psychometric process. Then we'll look at how to do load calculations for humidifier sizings based on those psychometric processes. And then finally, we'll look at different types of humidifier that are available on the market and where they may or may not be suitable for use. So the first part of the presentation is why humidify. So firstly, for improving productivity in industry and commerce. Now, if I were to sit here and talk to you about all the different industries I've worked in over my career, then we would have your families on the phone asking when you're coming home. So you can see from the pictures, there's such a wide range. Now, obviously, Condo is a global company, so not all of these applications you will see in every particular market. But just to briefly discuss some of the applications.
Dave sir, sorry to interrupt you. Your voice is coming little low. Can you speak a little bit louder, or you can open your video also?
Right. Okay. Is that better? Can you hear me? Hello?
Yeah.
Right, okay.
Yeah, now it's okay.
Right, okay, good. Yeah, so I've moved the microphone closer. So in India in particular, probably areas where most active would be the pharmaceutical industry. Obviously where drugs are being manufactured, it's very important that that's done in stable conditions. So low humidity, for example, when tablets are being coated, can give an uneven coating on the tablets. In the textile industry, obviously humidity is very important. It was mentioned earlier that fabrics, cotton, wool, jute, are all hygroscopic materials. So a hygroscopic material means that it can give off or absorb moisture in relation to the relative humidity of the air. So natural products tend to give off moisture to the air if the relative humidity is low. So things like cottons, wools will become brittle and more likely to break within textile processing machines. So a textile plant is a very good application for us in India. Get involved in the tea processing industry. Most of our customers are based in Assam in India. So in the processing of tea, they need very, very high relative humidity, up to 95, 98% for the processing of black tea to get the fermentation stage to happen correctly, and to reduce waste in terms of dust produced if the tea dries out. So again, it's a process industry where we're looking to improve the quality of the product, reduce wastage, and at the end of the day, improve profitability for our customers. Tobacco, print, again, both paper and tobacco are hygroscopic materials. So if relative humidity is low, the quality of these products are affected. But as you can see from the rest of the pictures, there is a very, very wide range of production industries where humidity control is especially important. The second application group that we get involved in is in preservation. So we talk about things like museums, art galleries, libraries, seed banks, churches. So a lot of these places have paintings, art exhibitions, that kind of thing. And these again are hygroscopic materials. So paintings in particular, very old paintings, you may have seen in a museum or an art gallery with an old painting, it might have lots of cracks on it. And these cracks are caused by variations in relative humidity. As the ambient condition changes, the canvas, or even in some cases on very old paintings, the wood that these are painted on expands and contracts as the relative humidity goes up and down. So this causes cracks to form. So it's very important for the preservation of very valuable artifacts that relative humidity is kept at a very stable state. In fact, for museums, it's especially important where you tend to find museums will loan each other exhibition artifacts for different exhibitions. And a museum, if it can't demonstrate that it has records of its environmental control within its galleries, they won't be able to loan artwork from other galleries. So it's very important that they are able to do this. And the third area that we're dealing increasingly with in terms of humidity control is health and infection control. So people, somebody who might work in an office or a call center, People are hygroscopic as well. We can give off and absorb moisture depending on the relative humidity. So in dry air conditions below 40% RH, the immune system efficiency of our respiratory system is reduced. In our noses and in our throat, we have little small hairs called cilia, and these are surrounded by a layer of mucus. Your throat is a wet surface, and these small hairs filter out impurities as we breathe in air. Now, if the air is allowed to dry, these filters effectively don't work so well. So we're more susceptible to breathing in aerosols, droplets, airborne particles that may contain viruses. And there's been a lot of studies done now that show that 40 to 60% is ideal for human comfort in terms of fighting germs. The second aspect of humidity for health control is to do with the actual viruses themselves and their float time. In very dry air, airborne droplets created by coughs and sneezes that may contain viruses shrink by evaporation and therefore are lighter and are able to float for longer. So this means that the spread around the building can be further. In ideal indoor air of 40 to 60% RH, they're heavier and they fall out of the air quicker. So coughs and sneezes don't spread so well around an office building. The third aspect is for the actual virus droplets themselves. As I said, these droplets, airborne droplets, contain viruses. As the droplets dry out, viruses are able to survive for longer. By maintaining relative humidity at a higher level, we don't get this drying out, and via a physicochemical reaction, the viruses are deactivated. Now, I am an engineer, a mechanical engineer, not a microbiologist, so I'm not the best person to explain this process in detail. But what I can invite you to do is to go onto the Condair websites, and there are presentations and information, especially by a lady called Dr. Stephanie Taylor, who is a doctor from the University of Harvard, who's done extensive research into this subject and gives some very good talks online about the actual biology of how this happens. And as I say, she can explain this in a lot more detail than I can. The next thing we'll look at is the EM Sterling criteria for human exposure to humidity in occupied buildings. Now, this has been part of the ASHRAE guidelines since 1985. So you'll see that for bacteria, viruses, fungi, mites, asthma, respiratory infections, chemical interactions, ozone production.
Dave sir, sorry to interrupt you. Dave sir, sorry to interrupt you. Hello.
Hello. Hello.
Hello. Dave sir, can you hear me?
I can hear you, yes.
Yeah, will you please open your video? I mean, that will be, open your camera, please.
Okay.
There are some requests from the attendee side that we are not able to see the speaker.
Okay, they'll be disappointed, but I will.
Yeah, it's
okay,
fine.
there we go.
You are quite handsome, sir. No issue. Thank you.
Can you see okay? Great. Okay, let me continue. Right, okay, to continue. So you'll see for all these criteria, and there's an optimum band of 40 to 60% relative humidity that that is best for human comfort. Okay, next we can look at industry guidelines from around the world, talking about relative humidity. Now, historically, there's been very lax regulation on control of humidity in terms of human comfort, but the recent global pandemic has really brought this into focus for a lot of people. So in the UK, government's documentations, they're recommending maintaining humidity above 40% RH. CIBSE is our UK equivalent, I suppose, to ISHRE, the Chartered Institute of Building Services Engineers. So again, they're saying humidity should be above 40%. The Health and Safety Executive in the UK is saying effectively the same things, but also in other parts of the world, in the USA, ASHRAE, again, saying maintain relative humidity between 40 and 60% RH. The European Centre for Disease Prevention and Control, again, are saying HVAC systems should maintain relative humidity between 40 and 60%. So you can see a very common pattern emerging amongst international groups working within the HVAC industry. They're all saying effectively the same thing. In Germany, it's the same story. In Australia, it's the same story again, 40 to 60% relative humidity. And even in India, I believe, the ISHRAE COVID-19 guidance document for air conditioning and ventilation issued in April 2020 stated that all things considered, the relative humidity level of 40 to 70% is considered to be the most suitable environment for humans and decreases problems in pathogens. In dry climates, do not allow relative humidity to fall below 40%. So there's an international consensus that relative humidity for human comfort and for disease control should be between 40 and 60% relative humidity. So next we'll look at the psychometric processes. Now I'm sure for a lot of you this is going to be a topic that you're very knowledgeable and familiar with already, but for the benefit of maybe some of the younger engineers, we'll go through the basics of psychometrics. So firstly, to look at the psychometric chart, there are a number of pieces of information we can get from this chart. So along the bottom on the x-axis, we have the dry bulb temperature. And then we have these curved lines, which are the relative humidity. So 20, 30, 40, 50% relative humidity, all the way up to saturation, which is this top curved line here. So by plotting a dry bulb temperature and a relative humidity, we can then take that point across to the y-axis, which is our moisture content. So this is the physical quantity of water in the air at that condition, and it's measured in kilograms of water per kilogram of dry air. So by looking at a point of temperature and a relative humidity, we can know how much water that contains. So the relative humidity is a ratio of the amount of water that the air contains compared to how much it can contain at that temperature if it was saturated. So to look at processes on a psychometric chart, first is a heating process. So you can see there from our start condition of 28 degrees C, as the air was heated to 45 degrees C, the temperature has increased. The absolute moisture content has increased because we haven't added any water into the air, but because the air at a warmer temperature, as it expands, it's able to hold more moisture. So therefore, the relative humidity drops from 50% as we started, sorry, 40% as we started, down to 15% relative humidity at the end of the heating process. So this is one of the most important things, one of the most important reasons that we have to humidify. There are two main methods of humidification. The first is isothermal humidification, So this isothermal obviously suggests that there is no change in temperature. And in the real world, this means adding humidity via steam. So to differentiate between the two different types of humidification, we have to look at the physics of what's happening to get the humidity to increase. So we have to get water to vaporize, to evaporate and be absorbed into the airflow. So obviously to get water to change state from a liquid to a vapor, we have to add energy. So with a steam humidifier, we're adding energy either through electrical heating elements, or we could be burning gas and putting it through a heat exchanger. So somehow, some way or another, we're adding energy to the water to take it to 100 degrees C, and then to change state at 100 degrees C from a liquid to a vapor. So what we're doing there is adding energy, getting the water to boil, the steam is being evaporated. Now, theoretically, the absorption of steam is an isothermal process, so there's no change in temperature. Now, in the real world, where we're probably going to have a metal pipe introducing the steam into an airflow, that pipe is going to heat up itself. So you may see a 0.5 to 1 degree C temperature increase. But in terms of the theoretical physics, we're not going to see any temperature increase. So it's called isothermal humidification. So you can see from our start point, we went from 40% relative humidity at 0.01 kilograms per kilogram moisture, up to 70% relative humidity at 0.017 kilograms per kilogram an hour. So as well as increasing the relative humidity, we've increased the absolute humidity or the moisture content. The next process is a dehumidification process. Now that's not the topic of the discussion today. We do sell dehumidifiers as well. So also a dehumidifier, rather than adding moisture to the air, we're removing moisture to the air. So again, it's a product group that's very relevant to the Indian climate, especially for the further south you get and the closer to the tropical parts. It's a very relevant topic to India. We actually have a second presentation that we can offer you that's purely about dehumidification, but I won't discuss that much today, apart from to say that during a dehumidification process, we're removing moisture from the air. The next process is cooling. So the first one is a sensible cooling process. So temperature is decreasing. As we decrease the temperature, it's the opposite of when we heat it. The relative humidity will increase. The absolute humidity will stay the same up until we hit the saturation line, the dew point temperature, and then the coolant coil will start to remove some moisture after that. And the final process that we'll talk about, and the other one that's of particular interest today, is adiabatic humidification and cooling. So here I'm talking about an evaporative and a wetted mat or a spray mist system, but we're using cold water. So we're not adding energy to the water by electrical elements or gas or anything like that. But we still need to do the same job. We need to remove, so we need to add moisture, we need to get water to change state from a liquid to a vapor. So in this case, that's done by taking that energy from the air itself. So we get a very different line on our psychrometric chart. As opposed to an isothermal process that we saw with the steam humidifier, here we see that we have a cooling effect. So the process line is actually up the line of constant enthalpy. So it's an adiabatic process. So here you'll see that as well as increasing the relative humidity and the absolute humidity, the moisture content, we've lowered the temperature. So this in hot climates can obviously be a huge benefit to us. For example, in a textile mill where a lot of heat is generated from the machinery and the weaving processes, to cool the air as we humidify gives an added benefit to the customer, as well as maintaining their correct level of relative humidity that they need for their process. It also improves the comfort for their staff in terms of temperature. And other applications such as data center applications, where server rooms, computers are generating a vast amount of heat, we can recirculate that air, pass it through an adiabatic humidifier, and as well as maintaining the relative humidity, we can also provide them with some low-cost cooling as well. That again is the subject of a different presentation called using adiabatic humidifiers for cooling. And again, that is one that we could offer to you in the future as well. So this next slide, now this is one that we prepared based on a winter condition that we might expect to see in Northern Europe, where we have very, very cold, low temperatures outside. Now, you're not going to see the kind of the -6-degree temperatures in India so often, I would suggest, but you may still see lower temperatures towards the north of India that make this relevant. So in the winter, we would bring in air at low temperature, -6 degrees C. Now, even if that air is saturated at 100% relative humidity, as we saw earlier, as we bring that air into the building and heat it to the temperature that we want for human comfort, we drop the relative humidity down to 15% RH. We've seen a huge drop in the relative humidity. So this, obviously, for process requirements or for human comfort, is a very, very low level. So what we then have to do is add steam to the airflow to bring our relative humidity up to 50% RH. So we can observe on the right-hand side of the psychrometric chart the extra moisture content required per meter cube of air. So from that, we can then calculate the humidification load. With an adiabatic process, now again, this is looking at a winter condition in Europe. There we go. You'll notice that because of the cooling effect, we've had to overheat the air to a temperature higher than we would want in the room to allow for that cooling effect. So where we use this technique in air handling units is where we've got maybe gas as the primary energy source compared to electricity. If you've got electric heating, then it makes no sense to do this. But if you've got a lower cost energy source, such as gas, you can use this for the heating to reduce your overall cost for the process. So these, as I said, these processes, although what's shown on the charts to you here is based on what we see in Northern Europe in cold winters, you can still apply these techniques to India. For example, with the isothermal process that we saw, one of our main markets for steam humidifiers in India is in the pharmaceutical industry. So a lot of the processes, they're supplying air at high temperature into tablet manufacturing machines. So they might be doing this at 40, 50, 60 degrees C. So you'll note that if you heat the air, even in a warm, humid Indian climate, if you heat the air from, say, 30 degrees at 70% relative humidity, if you heat that air to 50 degrees, you're dropping your relative humidity down to 20, 22% RH. So then we would want to add a large amount of moisture to give you a reasonable relative humidity for the tablet coating process. So even where you may think we have a very warm, we have a very humid climate, for certain applications, it's very necessary. We do a lot of work in Bengal area, in the jute industry. So again, where you have a lot of heat gain in the space, where you may have a warm, humid condition naturally outside, when the heat gain is picked up from all the machinery and you're increasing the temperature to maybe 40 degrees C, you've dropped relative humidity down to 40% RH. So then what we want to do is spray normally with a cold water humidifier up to 60–70% relative humidity. So that gives us the humidity condition we need for the jute, but it also gives the benefit of cooling for the occupants of the building as well. In northern parts of India as well, Delhi, Ludhiana, that up into Punjab, we have a lot of textile manufacturing customers. And again, a lot of these customers, they have dry periods of the year where humidification is required, or they may be using air conditioning systems, DX air conditioning systems, that are cooling the air. And as they cool the air, they drop it below the dew point, so they start removing moisture. So again, here we look at direct room humidification. So don't be fooled into thinking that because you're in a warm, humid climate, there's no need for humidification. There may be less requirement, but there's certainly lots of applications where process humidity control is necessary. And then that again shows the adiabatic process. As I alluded to earlier, we're also using cold water humidifiers in air handling systems to provide evaporative cooling, adiabatic cooling. So there are two main ways of doing this. In warm, dry climates, where we can look at direct evaporative humidifiers. So there we're bringing in hot, dry air from the outside. We pass it through an adiabatic humidifier. We cool the air as we increase the relative humidity. And obviously that is limited in humid environments. The amount of cooling we could get would be limited because we physically can't get the water to evaporate. So in that case, we can look at air handling systems with heat exchangers. So either a cross-flow recuperator, as you can see there, or a thermal wheel. So there we can put the adiabatic humidifier on the return air from the building before the heat exchanger. So we're cooling the heat exchanger rather than the incoming air. So by this means, we're getting some adiabatic cooling, but we're not adding moisture to the supply air to the building. So the benefit of this really is an adiabatic humidifier will use a lot less energy than an equivalent DX or chilled water cooling system. But as I said, that is the topic of a completely different presentation. The next set of slides is we'll look at load calculations. Now this is actually very, very simple. If we take an outside air volume of say 1 meter cubed per second, so this could either be being brought in via an air handling system, an air handling unit, or it could be natural infiltration through doors, windows, etc. But for every meter cube per second of air coming into the building, we can calculate the humidifier load by looking at the points that we looked at on the psychrometric chart. So we need to look at the ambient condition or the moisture content of the air before humidification, and we need to look at the internal design that we want to maintain, so the temperature and the relative humidity. And by looking at the moisture differential, we can calculate how much moisture we need to add per meter cube of air. We also need to consider the specific volume of the air rather than the or the density of the air, because we want to look at a mass flow rate rather than the volumetric flow rate. So the calculation is very, very simple. We look at the air volume, we multiply it by the moisture differential, Now, depending on what units we're using, we might need to multiply that by seconds per hour. So if an air volume is given in meters cubed per second, we would multiply that by 3,600 seconds. Generally, because humidifier loads are expressed in kilograms per hour or liters per hour. Then we would either divide by the specific volume of the air, which again we can take from the psychrometric chart at the point of the internal design, or we can multiply by the density, and obviously that is effectively the same thing because density and volume are the inverse of each other. So we're doing this brief calculation, gives us a duty calculation in kilograms an hour, or you may sometimes see this as well expressed in liters per hour. Obviously, 1 litre of water weighs 1 kilogram, so the two are one and the same. So it's a very, very simple calculation. Now when I started with the company 23 years ago, I had to do absolutely everything on a psychrometric chart, and I had to do all my calculations by hand. But the world has moved on slightly, and now we have selection software to do this for us. We have a Conde Help software where myself and Ashwini can calculate humidifier loads for you. So if you ever have a humidification project, as long as you give us all the relevant information, we can do detailed humidification loads and calculations for you, and from that select the correct size humidifier. There are a few rules of thumb we can use. Now the first one really relates to a cold winter climate. That says that for every meters cubed per second of fresh air, you need approximately 25 kilograms an hour. So that is based on the European climate where you have sort of cold winters and you want 2150 in the space. So that one probably doesn't really apply too well for an Indian market. The next rule of thumb relates to electrical steam humidification. So we're adding steam, boiling water by adding electrical energy to it. So for every kilogram an hour of steam added, we need 75 kilowatts of electrical input. Excuse me. So that actually is quite a useful thing because it affects what type of humidifier we're going to look at, whether we look at an electric steam humidifier or whether we look at an alternative such as a gas-fired humidifier or a cold water spray humidifier. Obviously, once you get above a humidifier load of 100 kilograms an hour and we start getting above electrical loads of 75 kilowatts, you know, that's a reasonable chunk of energy to be throwing at humidification. So once you get above that break point, you might want to start looking at a gas humidifier where the cost of that energy is less, or a cold water spray humidifier with a much lower running cost, and where we can use the cooling effect of the adiabatic process to give us some cooling as well. So we have a lower cost humidity and we reduce our cooling costs as well. So as a rule of thumb for the cooling, for every kilogram or litre of cold water evaporated, we get approximately 0.68 kilowatts of cooling. So that obviously, depending on the water temperature, changes slightly. That's based on about 20-degree water temperature. As the temperature gets up to 30, 40 degrees C, that figure will drop down to about 0.62 kilowatts. But it just goes to show that by evaporating even 1 litre of water, we get a lot of cooling produced at very, very low cost. Next, we'll move on to the main types of humidifier on the market. The first one, and possibly the most common that you'll see, is the electrode boiler. So on the moving picture, you can see on the right, we have a polypropylene type of plastic boiling vessel in which are positioned electrodes. Current is supplied to those electrodes, and it uses the conductivity of the water in the tank to pass the current between the electrode plates. The water therefore increases in temperature to 100 degrees C and then starts to boil. So steam is produced and comes out the top of the cylinder. So these tend to be one of the lower capital cost humidifiers on the market. But obviously, lowest capital cost doesn't necessarily mean the lowest cost to the customer over the lifespan of a humidifier. There are other costs we need to consider. The first is obviously the energy consumption. Adding electricity to boil water is quite an expensive process, so the energy consumption is high. The maintenance aspect is important with this type of humidifier as well. Water, as you know, when water is pure, it doesn't conduct electricity, so it requires minerals in the water which are naturally dissolved into the water to get the current to pass between the electrode plates. So obviously, because there are dissolved solids in the water, as the water boils off, these are left behind in the tank. So you'll see it in the form of scale, calcium scale. So that means there's quite a high maintenance commitment with this type of humidifier, in that we have to clean that scale out. So there are two types of cylinder available. There's a cleanable type and a disposable type. So a disposable type, once it's full of scale, you just take it out and you throw it away, which isn't necessarily the most environmentally friendly thing to do, and also has a cost associated to your customer. The other type is a cleanable type. So there you can take it out, you can break it down, clean out the scale and put it back in. So it's slightly lower in terms of the cost of parts, but there's still quite a regular maintenance time to do that. Certainly in a hard water area, you might need to do that every 1 to 2 months. So there's an ongoing maintenance cost to do this. In terms of control tolerance of humidity, you're looking at plus or minus 10% RH. So it's not the closest control humidifier. The reason for this is effectively to vary the steam output. We raise and lower the water level. That changes the surface area of the electrode plate that's covered by water. So then that changes obviously the amount of current that's passed and the amount of steam that's being produced. So we're effectively, because we're doing this on the inlet valve and the drain valve, it's not the most accurate way of controlling steam output. But that brings us on to the next type, which again is an electric steam humidifier, but it operates in a slightly different fashion. So you'll notice the first difference is that the tank is stainless steel rather than a plastic material, a polypropylene material. And this is because rather than electrode plates, we have resistive elements. So here current is being applied to the resistive element, and due to the resistance of that element, it heats up. So here we're having a direct heating effect on the water. So we're not passing current between the electrode plates, therefore we can use a metal tank. Now using a metal tank, a stainless steel tank, obviously has the benefit that it's going to be very, very long life in compared to a plastic. The plastic tanks, even if you use the cleanable type, you probably get 2-3 years out of it, and then the expansion and contraction, the heating and cooling means that the plastic will go brittle and crack eventually. With a stainless steel tank, obviously that is going to last for a very, very long time. The elements themselves, as they tend to be self-cleaning, so as minerals precipitate and start to form scale on the elements themselves, as they heat and cool, they expand and contract. So that causes the scale to crack off and fall down to the bottom. Now, Convair's unit has a uniqueness in that we have this item down the bottom, which is a scale collection tank. So as the scale cracks off the elements, it falls down through the hole in the bottom into this scale collection tank. So this means that even in a very hard water area, maintenance is very quick and easy. So you don't have to dismantle the whole tank. All you have to do is drain the unit down, turn this one way and then the other way on like a bayonet connection, drop this tank off, shake out the scale, put it back on. So it's very, very quick and easy. So obviously for process customers who can't tolerate downtime in their production, that's a huge benefit to them. The other benefit in terms of that is that because it's a direct heating effect, we can use treated water with this unit. So I'm talking about RO water, so water with all the impurities removed. So in this case, the scale build-up is very, very, very much slower. So you might expect to only have to do a once-a-year service, empty this tank once per year. So on a pharmaceutical plant, for example, that's a huge benefit to the customer. The other main benefit of this type of unit over the previous one on top of maintenance is the actual control tolerance that we can get. Because we can we just maintain a constant water level in the tank, and then we change the output by varying the current to the elements via solid state relays. So we can do this much more precisely, so we can get plus or minus 2 to 5% relative humidity. So plus or minus 5% would be the standard unit with mains water. If we wanted plus or minus 2%, there is a special process version that controls the current and the water level slightly more accurately, and we would need RO water as well. Because what we can do with RO water is reduce the amount of drainage needed. All steam humidifiers every now and again will go through a partial drain and fill cycle to try and flush scale and then elements out with it. Obviously, if we're using RO water, we don't need to do that so often at all, so we can get much higher control accuracy as a result. So where with the electrode boiler we might see that for general HVAC applications, comfort control, the resistive unit is we would tend to see more in process applications such as pharmaceuticals or museums and art galleries, where they need that high level of control and accuracy. We also have gas-fired humidifiers in the range. So here, rather than electricity, we're using gas as the primary energy source. So we have a burner, we're burning the gas, it passes through a heat exchanger that sits within a tank of water, and then obviously the heat exchanger heats the water, boils it. So benefits of this system over the electrical units is going to be typically in the energy cost. If you have gas available, it tends to be slightly cheaper per kilowatt than electricity. So the running cost of the unit is going to be lower. Again, we've got a stainless tank, stainless steel heat exchanger. So in terms of the maintenance and the spares, we can have good low cost to the customer. The typical control is plus or minus 5 to 10% RH, simply because the way the burners modulate, it's not as accurate as the control that you would see with a resistive unit. So again, it would tend to be more used for comfort humidification, where we don't need close control of the humidity. Now, the downside of this type of unit, I suppose, is that the actual capital cost compared to an electric humidifier is higher, and the installation is slightly more complex as well. So obviously we've got to have a gas supply in the building to start with. We've got to run that gas supply to the humidifier, and then we have to have a flue from the unit and to exhaust waste gases after the combustion process. So the capital cost of the unit and the installation cost is higher, but often in terms of the long-term cost to the customer over 5 to 10 years, it works out a lot better than electric steam humidifiers because of the lower cost per kilowatt for the energy. Next type is what we call a steam-to-steam humidifier. So many customers, particularly industrial customers or sometimes in hospitals, will generate pressurized steam for other processes. Now, this steam comes in two types. Firstly is clean steam, so this is pure sterile steam that you might see in a hospital or a pharmaceutical process. And then there's dirty steam. So dirty steam is where they're using town water to produce the steam, and there might therefore be chemicals added to that water to reduce the amount of scaling in the pressurized steam boiler. So that steam that the customer is already producing isn't really any good for humidification purposes, because those chemicals can be corrosive, and they can be an irritant to, if they get into the airstream supplied to a building. So in this case, we have a steam-to-steam humidifier. So the inside of this unit looks very similar to the inside of the gas-fired humidifier that we saw previously. So you have a stainless steel tank, and then you have a heat exchanger. So we pass the pressurized steam. Obviously, because it's pressurized, it's above 100 degrees. It's superheated steam. So therefore, it will bring the water to 100 degrees and it will boil it and at atmospheric pressure. And then you can add this pure sterile steam that you've generated via the heat exchanger to the airflow as you would with the electric system or the gas system as we've seen before. So this is a very, very good system to look at if you have an existing energy source on site. Now, the other type of steam that I mentioned was clean steam. So here we might see this in a hospital if it's used for sort of sterilization purposes, or in a pharmaceutical plant where they need pure sterile steam. And because this steam is clean, pure, we can use it for humidification purposes. So here we simply have a valve with an actuator. So the actuator opens and closes the valve, changes the flow of steam going into the sparge pipes, which you would see situated in the air handling unit. So this is good if you have an existing steam source available in a building that's suitable for humidification purposes. Now, with any steam humidifier, once we generated the steam in a tank, we then have to pipe it and we have to introduce it to the air somehow. So there are three main ways of doing this. The first two refer to air handling unit systems or ducted systems. So the first is a standard distributor pipe. There's not a great deal more to say about it than it's a pipe with holes in. So the steam would be connected to that. The steam humidifier would be connected to that pipe. The steam will come out of the holes, absorbed into the airstream. Now, sometimes you may need to absorb the steam in a very short distance. So this is possibly if you've got a low air temperature, or if you want to take the humidity to a very high level, or if you have a high velocity, or even if you just have a very short section within a duct or a handling unit in which to absorb the steam. So here you can look at what we call an optisorb manifold. So you'll notice the main difference is that where with a distributor pipe, we might just have one or two of these in a duct. Here we've got a grid arrangement. So we're introducing the steam to a much higher percentage of the airflow, so it absorbs much, much quicker. And the third way we might do this is if we have a small direct in-room application, we can just fit a fan unit on top of our humidifier. It will sit in the wall, it will suck in room air, mix it with the steam and blow it out the front. So there might be useful, just a small room application without a ventilation system, without a duct into which we can add the steam. So just to show you the difference between a standard pipe and a optisorb system. Looking at a random example where we want to increase humidity from 10% up to 50%, with the standard system, that might take up to a meter at sort of 20-21 degrees. If we want to shrink that down with the equivalent optisorb system, that would be down to about 250 millimeters. So you can pretty much quarter the evaporation distance required by using an optisorb system. So humidification distance is probably the number one thing that people get wrong with designing humidity control systems in ductwork. They don't consider the space it's going to take for the steam to absorb into the airflow. So there are a number of factors that will affect the absorption of steam. The first is the temperature, the temperature of the air, the air speed, the velocity of the air down the ductwork. Obviously, if the air is going quicker, it's going to take more distance for the steam to absorb. And also the change in relative humidity as well is relevant. Obviously, if you want to go to 90% relative humidity, you've got to add more moisture, and it's going to be more difficult to absorb than if you are only humidifying up to, say, 50% relative humidity. So all of these factors affect how much space you need to leave after the point of steam injection. So obviously, if you put your humidifier in front of a fan or some filters or a humidity sensor, you need to make sure that the steam is absorbed before it hits these components. Otherwise, you're going to start to get condensation forming, wetting, and that's bad, obviously bad practice. As I said, it's the #1 thing that goes wrong with designs of humidifier systems. But that again is where Condair can help you. Our selection software, as long as you've got all the relevant information, will calculate the evaporation distance. So we can discuss this with the AHU manufacturer or the ductwork contractor, and we can tell them what distance we need to leave after steam injection to prevent condensation within the ductwork. The next types of humidifier we're gonna discuss are the cold water units. So these were the adiabatic systems we discussed, and the first is an evaporative media type. So this is something you would have seen in India, certainly in various forms. So we're using the evaporation of water to humidify and cool the air. So the Condair system uses a glass fiber media positioned in the air handling unit. We have a hydraulic module at the bottom that pumps the water to the top of this glass fiber media. The water runs down as the air passes through it, evaporation takes place, and we get cooling and we get humidity increase. So where these units are especially useful is for large air handling systems where we want a high humidity load or we want to get a lot of cooling. So I would say globally, our #1 market for this type of system is in data center applications. So we've got very large quantities of air and we want to get cooling. So the benefit of using these for cooling in a data center application is that one of these systems we can make these very, very large. So we can make them 4 or 5 meter of width, 4 or 5 meter high. So a huge air handling unit and a huge air volume. And so the amount of cooling we can get can be hundreds and hundreds of kilowatts. But the electrical input to do that is going to be in the region of 0.5 to 1 kilowatt of electrical input. Because all we've got to do is provide enough electricity to run the control panel here and the small electrical pumps. So we can get hundreds of kilowatts of cooling for an electrical input of maybe 0.5 to 1 kilowatt. So obviously with data center customers where they're generating huge amounts of heat in huge buildings, the running cost savings to them by using cold water humidifier for cooling is huge. So this is something that sort of as the data center market is growing globally and will do in India as well, this is something that's being looked at more and more. The other good thing about this system is because all the evaporation is taking place within this glass fiber media, there's no evaporation distance as we saw with the steam humidifiers. So once the air leaves this glass fiber section, there's no need to leave space downstream beyond what you need to allow the maintenance access for the system. In terms of maintenance, they tend to be pretty good. There's no descaling as such. It takes quite a long time for this unit to start building up scale on it, and the control panel itself will go through drain and fill cycles to wash high concentration water. Obviously, as the water evaporates, minerals are precipitated and the concentration will go up, so the system will then activate a drain to wash these minerals away. So maintenance is very low on these, and in terms of components required, they tend to be very, very low. So in terms of the long-term cost to the customer, these are excellent in terms of energy and in terms of maintenance. Probably the downside for this is going to be the control accuracy, typically plus or minus 5 to 10% RH. That's because all we can effectively do is turn on and off the water flow to these pads, and then obviously it takes a certain time for the pads to dry out and the saturation to the evaporation to stop. And then once we turn it back on, it takes time for the water to fill up to the top and then to saturate these pads. So the control accuracy doesn't tend to be that great. If you want better control with a cold water humidifier, we would look at something like this, which is a high pressure spray system. So here we have a pump skid. This is generating water at high pressure, so sort of 70, 80 bar pressure. Then that's applied to the air handling unit via a series of control valves here. So then we would have nozzles mounted on the rack arrangement within the air handling unit. So by switching on different combinations of nozzle rows with different numbers of nozzles on them, we can get step control, either 7 steps or 15 steps of control. So that gives us control accuracy up to plus or minus 5% relative humidity. So much better control than you would see with an adaptive humidifier. The running cost is slightly higher because these high pressure pumps use slightly more electricity than the pumps on an evaporative system, because they're generating much higher pressure. So the running cost is slightly higher. The other downside of this type of system is really you do need to use RO water with the system. Otherwise, the nozzles will tend to block up quite quickly on sort of water with a high mineral content. So we do recommend RO water, which obviously does increase the cost of the unit compared to an evaporative system. So generally, unless you need close control, an evaporative system is a very good one to look at. If you need more accurate control, then this system is better. The other good thing about the Condair unit is you can run multiple air handling units from a single pump station. So we could have up to 4 air handling units, each with its own little controller, each with its own set of step control valves. So we can run up to 4 air handling units from a single pump station. So if the air handling units are in a common plant room or in the same location on the same roof, that can be quite a good cost saving to the customer. And the third type of unit we have in the cold water range that's unique to Condair is a bit of a hybrid system between spray and evaporative humidifiers. So here we have again a rack of nozzles mounted in the air handling unit, but here the pressure is much lower. It's only between 2 and 8 bar pressure. So the consequence of having a lower pressure is that the droplet size created, the aerosol size, is larger. So those droplets do take longer to evaporate. So that's why we have an evaporative pad at the back of the section. So any droplets that haven't evaporated in the airstream as a result of the spray settle on here and then re-evaporate. So what this effectively gives us is the best of both worlds. We have the better control tolerance of a spray system, but we have the short section length that we're going to get with a spray system. A spray system obviously does have a certain section required to evaporate. With the high pressure system, that could be sort of 2.5 meters. So we need quite a long section in the air handling unit. But with this hybrid, because we've got the evaporative media, we can get a section down to 600 to 900 millimeters. So obviously, in terms of the cost of producing the air handling unit and the space required in the plant room, this is going to be the shortest section length of any cold water humidifier. And we can get close control plus or minus 2% RH. We can go up to 31 steps of control with this system. So very, very close control, short section length. It's an excellent humidifier. But sometimes, as well as looking at HVAC solutions, we do need to look at in-room humidification systems as well. So this might be for textile areas, print rooms, tea facilities, tobacco factories. So somewhere that we want to spray moisture directly into the air stream. And here, this particular type of nozzle uses water and compressed air. So the benefit of using compressed air is that it gives us a very, very fine droplet. So it's absorbed into the airstream very, very quickly. The droplet size using compressed air is much smaller than just by using a high pressure nozzle system. So it's, as I say, it's great for factory environments where we don't have a ventilation system, or even in some cases where we want to complement a ventilation system. For example, in a lot of textile manufacturing, they might have a full ventilation system supplying air at a very low temperature, sometimes down as sort of 12, 15 degrees. Now that's to allow for a massive heat gain off the textile manufacturing machinery. Now, because that air is being supplied at a low temperature, it physically can't hold enough moisture to give us the sort of the 60–70% relative humidity we want at our room condition of 20 degrees. So here we have no choice but to use an in-room humidifier. So this sort of system is perfect where we have a ventilation system not suitable for humidification, or indeed if we have no ventilation system at all. So here we can get typical control of plus or minus 4% RH. And the final type of unit that I'm going to talk about today is where we use a high pressure system in an in-room application. So you'll notice on the video that's playing, rather than just having a nozzle, we have a fan as well. So that's just to help spread the moisture around and prevent it drifting. A high pressure nozzle, if you just have the nozzle directly into the air, it will tend to just drift wherever it wants to go, because it doesn't have the motive force behind it that we'd see with a compressed air system. So that's fine if you've got a very, very high ceiling. You can mount the nozzles at high level and you can allow the mist to drift down and evaporate as it drifts down. But if you've got lower ceiling and you don't want that mist to come down, you can use one of these systems with a fan to distribute the moisture and that kind of thing. These tend to be used more in cleaner environments, I would say. I don't know if any of you have ever been into a textile mill or a jute mill or something like that. There's a hell of a lot of dust generated in the forms of textile fibers. So everything gets covered in dust, including any humidifier that we put in there. Now, the compressed air and water nozzles are very, very good in that the dust will collect on them, but because of the non-stick coatings on them, the maintenance required is you can just blow the dust off, and that's fine. Obviously, with this type of system with fans, electric motors, these would very quickly become clogged with that. So you wouldn't use it in a very dirty environment. We don't typically use them in textile applications, but for things like the video showed there a fruit and veg area of a supermarket, or cleaner manufacturing environments like electronics, that kind of thing, it's a very, very good option. So the last slide is really just to tell you about some of the resources you can find on the Condair website. Now, obviously, you can find information about all the different types of humidifier that we sell, including technical manuals. You can find BIM files so that you can drop those onto CAD drawings. There are spare parts lists. There's a basic psychrometric calculator. So if you put all the information in, it will do you a duty calculation. Although obviously for a detailed calculation and a selection, you should talk to my my colleague. And also there are a lot of application pages as well. So for all the things I may have mentioned, T-Textile, HVAC, cooling, data centers, there's an application page. And so it tells you what the best solution is for every different humidification need. So you can find all those services at www.condair.co.in. In terms of services that Condair offer, so we design and manufacture all of our own equipment. We can offer installation and commissioning services, as well as my colleague Ashwini, who's based in Delhi, who handles the sales side of things. We have two long-standing partners in India. The first is Humidity Technologies, based in Mumbai. So they focus very much on the pharmaceutical industry, but also look at other HVAC applications as well. So Mr. Sridhar Gokali there has a huge amount of experience in humidification, but also in general HVAC and contracting as well. So his organisation are able to supply, install, commission humidifiers. Then we have another partner in Calcutta, Mr. Jaideep Dasgupta of Regent Machine and Servicing. So they focus more on direct room humidification. So they handle the textile, jute, tea, tobacco industries for us. So again, they will kind of install and commission on behalf of our customers if need be. So it's not just the case that we want to sell a box and thank you very much, Mr. Customer, and walk on. What we want to do is work with our customers to give them service for the whole life of the humidifier. So we can put you in touch with people that can take part in servicing for you, supplying spare parts, technical help when needed. We're there for the customers for the whole lifespan of the humidifier, not just on day one when we sell you a humidifier itself. That concludes the presentation. As I said, my name is Dave Bull. I'm based in the UK and I provide technical support towards the Indian market. My colleague Ashwini Anand is based in Delhi. He is the business development manager for Condair India. He is available to you on a day-to-day basis should you have any questions. So he should be your first port of call, and then he brings in whatever resources are needed to get the job done for you. And we do have two other presentations that we could potentially do for you in the future if interested. The first is in the subject of dehumidification, and the second is using cold water humidifiers for evaporative cooling in air handling units. So if invited back, we would be delighted to do those for you. And that concludes my presentation.
Thank you, Dave. It was very wonderful and the explanation was very good. I hope everybody understands about the humidification, though everybody knows about that, but the detailed understanding would be there. So I would request participants, if there is any questions, so please let us know so that we can answer here. Mr. Tapas, is there any questions?
No, sir, as such, I'm not finding out here.
Okay.
I think a participant will comfortable to ask directly to you, or
no issues.
in email ID, they can send us to delhichapter1981@gmail.com.
Okay.
Or number is reflecting here. I will share your email address in detail also for the
Sure.
further queries.
Sure.
Whatever the attendees we have received, we will
Yeah.
send all the details, your number and your email as well for further
Sure.
queries directly to you, or they can send us also. We'll forward to you.
Sure.
Perfect.
So I think it was wonderful presentation, Mr. Dave Bull. It's a great pleasure that you have spent your time here. And I think this is just a start. We'll have more collaboration with you for this kind of program, and we'll happy to make this kind of program in future as well. Any final message, Ashwini sir, Dave sir, you would like to share in this forum so that we'll further proceed for vote of thanks?
Yes, it's a very privilege for us to, presenting ourselves at the platform of the Delhi chapter of ISHRE, because it's a very big and huge platform for the HVAC industry. So we are delighted to have our product presentation here at your platform. And we would like to present, as Mr. Dev said, that on the dehumidification and on the cold humidification systems also in near future. So we'll get in touch with you to get the appointment for the prescribed date, and we will check Mr. Dev's calendar also. So accordingly, we definitely will do that presentations also. But that was a wonderful thing what we did, and we got your support to do that. Thanks a lot.
Thanks, sir. Our pleasure. Thank you very much.
Yeah, thank you very much for your time.
Yeah.
It's a pleasure to speak to you all.
Yeah. Yeah.
Thank you. Thank you very much. Thanks a lot.
Thank you.
All the
Bye.
participants to join. Thank you.
Thank you, sir. Further, I request Dr. Pratima Singh with us. So I request ma'am to further execute vote of thanks for this session. Thank you. Please proceed, ma'am. Thank you.
Thank you, Tapas, and thank you, everyone. And it is my privilege to have been asked to propose this vote of thanks for today's product presentation on humidification and psychometrics. And I, on behalf of Delhi chapter of ISHRE, our supporting partners, ISHRE India chapter, Prem Jain Memorial Trust, Ras Vadodara chapter, and the entire organizing committee. And on my own behalf, I extend a very hearty vote of thanks to our esteemed speakers, Mr. Dev Bull, Applications Manager, Condair Global Sales, and Mr. Ashwini Anand, Business Development Management Manager, Content India, for enlightening us all with their knowledge and wisdom in the area of humidification and psychometrics. Thank you so much, Mr. Bull, for briefing us about various ways of improving productivity in industry and commerce, which is very important for any organization. Role of hygroscopic materials, ideal humidity range in indoor air for improved health and infection control, and how relative humidity affects virus flow time and virus survival time. You also highlighted on optimum RH ranges for enhancing the health comfort, recent industry guidelines on indoor air, maintaining it to RH of 40 to 60%, as spread of infections is reduced if we maintain a suitable humidity levels. Various methods and products which are available for humidification and dehumidification, evaporating cooling strategies, load calculation formula, different humidifiers and their benefits and considerations. It was a very interesting product presentation on different humidifiers and the various services which the Condair gives to its users. So I would like to also extend a very heartfelt thanks to Mr. Ashwini Anand and to all the participants for the patient hearing. Thank you so much, everyone. Yeah, Tapas, you can take over from here.
So thank you very much, ma'am. Thank you, everybody. Thank you for joining this session. Aswini, sir, should we close this session with your permission?
Yeah, definitely.
Okay, thank you.
Okay, thank you very much. Thanks a lot, Mr. Tapas, for your handling everything very smoothly. Thanks a lot.
Okay, my pleasure.
Thank you.
Thank you.
Thank
Goodbye.
you.
Have a nice evening.
Thank you. Bye.